Hi there, thanks for tuning into this video here. On this short video, I hope it's short anyway, we're going to talk about three things, some area formulas, and then I'm going to show you kind of a cool connection between the slope formula and the distance formula. That is, given a couple of point coordinates, using the slope formula and the distance formula for just those pairs of points. Okay, but first we're going to take a look at some area formulas, and we will start off with the most basic of geometric shapes, in my opinion anyway, which is the rectangle. The rectangle, you measure the two sides, base and height, and as long as it's got four square corners, it doesn't matter how long the base or the height is, it's a rectangle. And to find the area, well, you probably already know what to do, but I just wanted to show you a couple of other things here. There's a couple more rectangles. Sometimes they may be tilted, and but the base and the height are still just the lengths of sides on the rectangle. You might have to use your distance formula and come up with some kind of square root numbers for the base and the height. But the area, as you know, for a rectangle is just the base times the height. Pretty simple, very basic thing to do. And coincidentally, there's another shape that uses the exact same formula. It's called the parallelogram. All right, parallelogram also, one side is called the base, but the height is not one of the sides. All right, the height is actually this perpendicular distance between one side, called the base, and the side opposite. Those two sides are parallel, and that perpendicular distance between those two parallel sides is called the height. So that's the only tricky part about a parallelogram, is finding the height. It is not the length of one of the sides. Generally. So, but then the area formula is still the same thing as a parallelogram, base times the height. So you get two shapes with one formula there. Pretty nice. Let's move on to the next, and probably certainly one of the most important shapes in all of geometry is the triangle. Now you may already know the formula for the area of a triangle. Here it is. It's 1/2 the base times the height. And I thought we'd take a little bit of time just to explore as to why the formula is what it is. Where does that 1/2 come from, and base and height and all of that? Okay, well, let's start off with a rectangle. And we've got our base and our height there marked off on the rectangle. Now what I'm going to do is divide that rectangle in half by drawing a line from one corner to the other. Hopefully you saw that that was definitely 1/2 of the rectangle. The rectangle is base times the height, so the triangle is 1/2 base times the height. So there's a right triangle. The base and the height are two sides of the right triangle, called the legs, as a matter of fact. And so you multiply those together, 1/2 times that, and that's your area. Well, let's take another rectangle here, and this time we're going to draw a triangle inside the rectangle. And I'll show you that it is still 1/2 the base times the height. If you took that upper left triangle there and kind of folded it over, let's say, into the triangle. Okay, think of that. Think of what just happened right there. I folded that upper left corner over the edge of the triangle into the triangle. I'm going to do that again on the right side. Watch this again. So take that, and it just folds right in there. All right? What I did was I took the whole rectangle, and I've collapsed it into the triangle. The triangle is exactly 1/2 of the area of the original rectangle there. So the formula, 1/2 base times the height, it applies to whether it's a right triangle over there or whether it's like an isosceles or some other kind of scalene triangle there. The height times the base divided by 2 is another way to say it. Okay? Take a look at this. The parallelogram, whose area is also base times the height, can also help us with the triangle formula. So there's a parallelogram. I've got the base, I've got the height there, that perpendicular distance. What I'm going to do first, though, is kind of move that height over, so move it outside the parallelogram. But once again, I'm going to draw a line connecting the parallelogram and dividing it into two equal parts. Okay, so that parallelogram has now been divided in half. And now I'm going to remove that top part, and look at that, the area of that triangle. Look where the height is. That's what I wanted to show you. The area is still 1/2 the base times the height, but the height is over there outside of the triangle. Okay? But all of those triangles that we've drawn, the right triangle, the isosceles, or it could be a scalene triangle, and this obtuse triangle, all use the exact same area formula, 1/2 the base times the height. Okay, last shape. is the trapezoid, and there's a picture of a trapezoid right there. You know what that shape looks like. You've seen them before. Let's see. Here's the trapezoid has two pairs of parallel sides. All right, and they can be like that, or they can be over there like that. Those two vertical sides now are the parallel sides. They're both trapezoids. Now, I wanted to say a couple of comments here about the trapezoid before we get into the area formula. The two parallel sides of a trapezoid are called the bases. All right, so wherever they're oriented, whether they're horizontal or vertical or some other direction, the two parallel sides are called the bases. We call them base 1 and base 2. We use those in the area formula. Also, the height of a trapezoid is used in the area formula, and that, once again, like the parallelogram, is the perpendicular distance between the two parallel sides. All right, so that is what the height is. It's the perpendicular distance between the two parallel sides, or between the two bases. I even wrote it in purple language there for perpendicular. Anyway, so on that one right up there above the writing there, you see the height is going up and down, but it could go right to left. It just has to be perpendicular to the parallel sides. Okay, so once you've got the bases figured out and the height figured out, then you're ready to use the area formula, which is 1/2 times the sum of the bases. So add up base 1 plus base 2, and 1/2 of that sum times the height. Okay, that is the area formula for a trapezoid. 1/2 the sum of the bases times the height. Sometimes people call that the average of the bases times the height, because you're taking the sum of the bases and dividing by 2. Base 1 plus base 2 divided by 2, or 1/2 times the sum, is the same thing. So there's your area formula for a trapezoid. All right, so we won't be doing any examples of these area formulas in this video, all right, because we kind of got a lot to cover, but I think we've been talking about that a lot in class, so hopefully you have enough to go on. Let's move on to the next topic, which is dealing with the slope formula and the distance formula, and I want to show you how those two things are kind of connected. All right, let's take a look at the slope formula there. The slope, m, usually is called the slope y minus y over x minus x, and you could throw in the 1 and the 2 there for y1 minus y2, x1 minus x2, and we call that the rise over the run. The rise is the y's, y minus y over x minus x, the y's on top, the rise on top, y's is the rise. Okay, that's the slope formula. Now, the distance formula is a little intimidating looking. It's got the big square root sign, big radical there, but look, it uses y minus y and x minus x. It uses the same things as the slope formula, except that in the distance formula things get squared and added up instead of simply divided like they do in the slope formula. So you can throw in the x1 and the y1 and all of that, those little subscript numbers in there too, of course. But let's make this notice here that y minus y over there is the same thing as y minus y over there in the distance formula. And the same, except the difference is that we square that difference. Okay? We square y minus y2. For the x's, it's the same exact thing. x1 minus x2, x1 minus x2 in the distance formula, and we square that difference. Okay? And then, of course, we add them up and just kind of leave them there under the radical, or if we need to, we can use a calculator. But let's do a quick example here and show you this. Let's say we have a couple of points, 3, -5, and 10, 6, and I'm going to use them in the slope formula first. So I'm going to take y minus y and over x minus x, and notice that I went in the same direction for both the top and the bottom of that fraction. That's very important. Okay, and what does that give me? Well, it gives me a -11 over -7, so a nice rhyming fraction, 11 over 7. That's my slope between those 2 points. Now, if I figure out the distance between those 2 points, I'm going to use exactly the same numbers. So y minus y was -11. I'm going to take -11 and square it, and that's part of my distance formula now. And I'm going to take the x terms there, -7 squared, and put that underneath my radical. And so 11 squared is 121, 7 squared is 49. The negatives kind of drop out when you square them, by the way, so don't worry about that too much. And 121 plus 49 is 170, so that's my distance, the square root of 170. Okay, so I kind of got a lot of information just from those two coordinates, just by taking the difference between the y's and the difference between the x's. Okay, let's do another quick example to show you how that works. Here's 2 points, -6, 10, and 15, 44. So let's find the slope first. 44 minus 10 over 15 minus -6, that's 34 over 21, because 15 minus -6 is just like 15 plus 6. So there's my slope, 34 over 21. That doesn't simplify at all from there. My distance, however, is going to use the exact same numbers. I'll set up my radical, and it's going to be 34 squared plus 21 squared. See, I got that straight from the slope formula. All right? I've got, that's 1156, that's 34 squared, plus 441, that's 21 squared, and I take the sum of those two things, 1597, and the square root of that is pretty doggone close to 40. The square root of 1597 is 39.96, and that's my distance between those 2 points. Okay? Well, I hope that was helpful. Take care now. Go do some math. Oh, yeah, and that extra credit question. I would like you to tell me the 4 original color and shapes of the marshmallows in Lucky Charms. The 4 original colors and shapes of the marshmallows in Lucky Charms cereal. Okay, bye-bye.